So in the spirit of wise men agree and fools seldom differ, you will hear a lot of things today from me that you've heard from the previous speakers. I tend to come at it from a slightly different perspective, and I'm probably going to disagree with some of the things that other people have said, so bear with me. This is not a technical talk, and I have a special bonus for you. You're not getting one, but you're getting two, count them, two talks today for the price of one. I have a little talk that goes beyond SQL that I'll give at the end, which I think may shed some light on actually doing big data analytics projects. So I'm going to talk about some of the things that other people have talked about. When is data big? What are the standard approaches in big data analytics? And then I'm going to talk things about more than technology, how do you start, etc. So you may have heard this before, but data is big when you cannot solve your problems. When either queries or jobs, whatever it is, run way too long. Particularly when data loading takes way too much time. I frequently hear people with big data analytic warehouses saying, you know, I've got this 3-hour window every night to load my data, and I'm up to 2 hours and 58 minutes now, and my data is only getting bigger. What am I going to do? Or when the kind of analytics you want to do either take too long to do or simply can't be done. And while big data means many things to many people, what it means to me is doing analysis on that data. And there are other things you can do with data as well. And it's about being able, you know you've got a big data problem when there are questions that you want to ask that you can't ask them because of these impediments. It's also when costs are too high. So a lot of movement in big data analytics has been not so much in response to lack of capability, but in response to particularly high software licensing costs and associated hardware costs and associated development costs and associated support costs. So we can do some of these things in traditional methods, but we can't afford to do these things in traditional methods. So you may have heard this. What's big data before? Well, it's particularly when you've got big volumes, but you've got big data types, and by big data types, we have come to mean this is, quote, unstructured data. You will hear my rant on unstructured data in a few minutes. I don't actually believe there's unstructured data. I think unstructured data is noise. I think if it's data, it has structure. It may not be relational structure, but there's structure there. I can look at a movie and understand the structure, but it's not SQL. And finally, it's velocity. There's new kinds of data from new devices, but I know people who have a relatively small database in what I would call their fixed size, but every day they're ingesting 100 terabytes of data and then, you know, throwing it out a week later. So a lot of stuff goes through their data analytics system, but it doesn't stay there very long. So in the beginning, actually not quite the beginning, in the beginning everyone had their own system. There were no standards. If you had a data set that worked with one analytics program, it didn't work with another analytics program because it was in the wrong format. But in the spirit of standardization, people started storing their data in relational database systems. These things ran on large symmetric multiprocessors for the most part, and people like Uncle Larry, pictured up there, would tell you about all the miracles that you could do with your data. And what happened was that, you know, a relational database system and SQL was a place to get started, but to do any meaningful work, you needed to put lots of stuff on top of that. You needed to put ETL tools, you needed to put on BI tools, you needed to put on some sort of descriptive statistical analytics. And over the course of the years, there grew a community of people who understood how to use these tools. And things were going on very nicely, thank you. We were doing great analytics, but something happened. Maybe 10 years ago, it's hard to know exactly when it happened. People became annoyed with the cost. The cost of extremely large machines became very high. There was a performance bottleneck with lots of different architectures, and there was the rise of something called unstructured data, by which I mean non-SQL data, but data that's incredibly valuable to the enterprise. And I want to make this point because sometimes when I say this, people think I'm being negative about SQL. I worked for Oracle for a long time, and as they used to say on Saturday Night Live, Oracle be very, very good to me, you know. And truth be told, SQL is actually very good for lots of stuff. But as one of the commentators mentioned, there's no silver bullet, there's no technology that works for everything. And as a result of that, different things, different things happened. So what were the performances or issues with SQL? One is that queries began to take longer and longer as the data set grew. And in spite of faster disk subsystems and better optimizers and better schemas, things were taking too long. There were the queries that went out there into never land and never returned at all. That were interesting queries for the business. Loading, as I mentioned, couldn't fit into the loading window. And another problem, which is that traditional statistical-based analytics were traditionally done in an analytics platform which was distinct from the database. So the model is we go into the database, we select some data with a select statement or a loader statement, we then take that, we push it into an analytics platform which runs someplace else, usually in memory. And that has a number of drawbacks. Drawback number one is it takes time to unload that data and move it. And the other thing is, when you have to run something in memory, you are limited to doing analytics on the size of the memory you have. The biggest machine I've ever used has got 2 terabytes of real memory. It was a great treat to use, but those machines are very expensive and few and far between. And 2 terabytes these days is a kind of modest size, big data analytics data set. So people would do sampling. And as we all learned from Statistics 101, we all learned this from Statistics 101, that, you know, taking a big sample has got some interesting properties that, you know, your estimates of mean and variance, that all drop as the sample size increases. And for doing certain kinds of descriptive statistics, that's fine. But if the kind of analytics you want to do involves finding rare events or creating networks of people and events, and if you miss some of the points, you can't connect the dots properly, statistics is not your friend. So those were some of the technical problems. And then there were some cost problems. Traditional database vendors price by the CPU. And increasingly, the issue became, we don't need more CPU power per se, we need more I/O power, but the way to get this is to buy more CPUs, and Uncle Larry, the wizard you saw on the last slide, is getting another 125-foot or 225-foot yacht based upon what I'm paying every year for maintenance. So, was there salvation in SQL? And the answer was yes. 5-7 years ago or so, there became a collection of MPP, massively parallel processing databases. And as it was described in the keynote this morning, there's a series of small servers. We distribute the data across the servers. Queries run in parallel across the servers. Loads run in parallel across the servers. There was a mention, I'll take exception with something said this morning about there were columnar orientation databases that stored stuff by column rather than by row. And running stuff by columns was great because in terms of compression, there are a lot of similar values in a column of a table, not so much similarity across a row, so we could get much better compression ratios, which means that the data set took less space to store, which means we could store more of it, which means when we had to analyze it, it took fewer I/Os, so it could get quicker. But there's a cost for everything. There's certain kinds of queries in which columnar orientation works extremely well, and there's certain kinds of queries in which storing stuff by rows works well. So for a quick, shameless product plug, and I promise not to many of them, the little company I work for, Greenplum, which was acquired 2 years ago by EMC. Boom. I used to work for Oracle. I'm sorry, that was a serious faux pas. Gives you a choice of storing a table either in a row orientation or a column orientation, depending upon what suits your analytic needs. And also, in these small SMP companies, all of which actually have been bought out by other companies now. There were 5 of them. Microsoft bought one, EMC bought one, HP bought one, IBM bought one, Teradata bought one. So the 5 little SMP players are all now part of something else. But a lot of these had the ability to run analytic statements directly in the database, which means you could, 1, run them on the entire data set, and 2, is you didn't have this process of pulling the data out, moving it someplace, analyzing, pushing a result set back into the database. And that was good. And there are alternative pricing models here that are predicated upon the size of the database rather than how many CPUs you've got, and they're lease models rather than purchase models, et cetera. So there was an opening in this market, and that was a good thing. However, there was the rise of the NoSQL movement. So the rise of the NoSQL movement had some objections to SQL. Some of them are perfectly justified. Some of them are rants, my opinion. So it doesn't handle unstructured data. And if you examine a lot of the use cases that NoSQL databases actually work on, those things can be handled quite easily in SQL, okay? That's not the real reason. Now, there is some stuff, and there's lots of stuff that SQL does not do well. SQL does not do text analytics very well. Try doing image analysis in a SQL database. Impossible, et cetera, et cetera. So there's some justified exceptions to this. It doesn't scale to handle big data. Well, big SMP boxes don't scale well, but these small SMPs do actually scale well. It costs too much. There's a lot to be said for that. Here's an interesting point that most big traditional databases, with a few exceptions, have features built to do OLTP, online transaction processing, which are completely unneeded in an analytics environment. And so there's bloat in the product. Code path gets too long. The very fact, even if you don't exercise these features, the fact that they are in the database code itself slows stuff down. And then there are the people who said, I hate dealing with company O. I can't stand company M, and I particularly loathe company I. Choose the letters you want in any order, but you've heard these people, okay? And as mentioned before, these things are not agile. They said, when you do a big SQL implementation, you've got to get the data layout and the data model first, then load the stuff in. And if you've done it wrong, you're back to square one and you do it all over again. Whereas in these so-called schema on read NoSQL models, we just make the stuff up as we go along in a good way, not a bad way. So, and also, we don't handle unstructured data well, we don't handle text processing well, we don't handle streaming media well in SQL, so we are going to give up on SQL. There's a very interesting, but not for those who don't like offensive language, video on YouTube. If you go to YouTube and look at MongoDB is web scale. It's a little cartoon with a rant from someone in the NoSQL movement who tells you everything that's wrong with SQL. Of course, everything he says is wrong, but never mind. So a wealth of NoSQL technologies came. And by NoSQL, we mean they don't fit into a relational database. Some of them actually use SQL, okay? But they're not underpinned by a relational database. And the winner of the moment is Hadoop, which has a huge lead. Hadoop's logo is the little yellow elephant. The little yellow elephant was named Hadoop, was the toy stuffed animal owned by the son of one of the founders, not the founders, the originators of the Hadoop project. Okay, so that's why it's called Hadoop. He wanted a word that didn't mean anything. Hadoop was just as good, so Hadoop it is. So, and it was inspired at Google by two projects, Bigtable and the Google file system. And it arose out of lots of needs at Google, like the ability to index the internet every day, every hour, every 4 hours, however often they do it these days. It's got to be scalable because the internet was growing in leaps and bounds. So Hadoop has to have this cluster property that when you run out of horsepower, you just add a few more nodes into the cluster. And literally, that's what they do in these big places. They just go out and they order another 100 nodes and plug them into the cluster and redistribute the data. You've got to know that Hadoop is not an OLTP, not a real-time processing unit by any stretch of the word real-time. You're not going to keep airplanes in the sky with Hadoop. Okay? You're not going to do your HR system database on Hadoop. But you are going to do analysis of data related to keeping airplanes in the sky and your HR system, et cetera. It's got to be fault tolerant because we distribute everything. If you lose a portion of the cluster, you've got to make sure that that data is someplace else that's taken care of. It's built on inexpensive commodity hardware. That's codeware for an Intel machine with traditionally these nodes have 1 or 2 CPUs, 4 to 6 cores, 16 to 64 gigabytes of memory, and their own directly attached storage systems. So even though the company I work for, EMC, is a manufacturer of shared disk subsystems, we're in the Hadoop business doing it this way. And the data is distributed and replicated. And as mentioned before, when you do something in Hadoop, the goal is to push the analysis to where the data is. There's something called the name node that knows where each copy of the data is. And when we want to analyze it, we push the analysis to that node where the data that we want to analyze is located. Okay? And so there are other players in this game. They've not been quite as successful, but they have slightly different purposes. So what's in a Hadoop cluster? Anyone here a Hadooper? Okay, so Hadoop cluster consists of actually 3 things. One is a distributed file system. So we have this file system which is not your standard POSIX compliant file system. It's completely different. The semantics are quite different. The way of accessing is quite different. And we make multiple copies of our data, traditionally 3 copies of every single big block of data. And this is for analyzing big files. Hadoop is not well suited to gazillions of small files. It's better suited to millions of big files. And then there is a framework for writing programs. It's called MapReduce, and it consists of mappers, which you might think of as feature extractors. They examine some data and they extract some feature from it. You read a line of a file, you extract a couple fields from it, etc. Then the mappers feed stuff into the reducers, and the reducers take the results of the mappers and organize that into some sort of coherent structure, and that's written back to the Hadoop distributed file system again. And in order to do this, you need tracking mechanisms to figure out which node is working on which piece of data, and if it fails, where to start it again, et cetera, et cetera. It's not easy to write MapReduce code. There are very few people who can do it. It's all written in Java, okay? Once you see how to do it the first time, it's a lot easier to do the second time. But if If writing shell scripts is like riding a tricycle and writing SQL code is like riding a bicycle, then writing MapReduce code is like riding a unicycle, or perhaps a half a cycle, whatever that might be. So as a result, the Apache project, which runs Hadoop, this is an open source project, put a whole lot of tools on top, high-level languages to get you started so you can do things. They're not quite as efficient, but they're much easier to write. So I know people who've written pig or hive jobs to do something in a few hours that had they written MapReduce jobs would have taken them 3 days to a week to do. Okay? They don't run as efficiently, but development time costs too. So that's the trade-off you have. A Hive has SQL-like access to data, but if you're going to be consistently doing SQL, it is much slower by 2 orders of magnitude than loading stuff into a high-performance relational database, the kinds of joins you're going to do. So an HBase is now very popular as a sort of the database of choice in Hadoop land, and it's very good for large, sparse tables. It uses what is known as key-value pairs. You can read about it at your leisure. So this is what Hadoop does. You submit a job on the left-hand side. It goes out. It finds some mappers somewhere. You tell it how many you want, not where they are. The mappers all produce stuff. They hand it to a reducer or a set of reducers, and that produces some output, which then gets stored someplace. This is sort of like cloud computing. You submit a job somewhere to your cluster. The job tracker figures out how many nodes, well, you tell it how many nodes you need. It figures what's free at the moment, where of the 1,000 nodes in your cluster it's going to run your particular 10 or 20 or 30 nodes. Assign stuff to the mappers. Stuff gets sent to the reducers, written out someplace to the file system. Somewhere you have no idea which physical node it's on. It's just out there somewhere. This is cloud computing of a sort. Okay? I think this is the first mention I've heard of cloud computing at this conference, so I thought I would mention it. What's the killer app for Hadoop? So some people think it is ETL, extraction, transformation, and loading. And the notion is that you've got huge amounts of data coming in from various places, of which possibly only a small fraction of it is really of interest. The rest of it is stuff you got to go through to figure out if it's of interest. It's sort of like mining for gold. You go through tons of dirt to find the odd nugget. And Hadoop is particularly good at assigning lots of these small commodity Intel-based hardwares to go through this. They go through lots of data. They find the good stuff. They throw out the bad stuff. And they put it in a file someplace, and then you can do something with it. So there are a lot of people who think that, at least in the short term, the killer app for Hadoop is doing ETL, rather than doing ETL the way that it is traditionally done in the data warehousing world. So a couple things that it would do is fraud detection. So in the Hadoop world, there are things that are called supervised learning and unsupervised learning. In supervised learning, you have lots of data. You divide it, let's say in the case of fraud detection. This is examples of fraud. These are examples of unfraudulent activity. I want you, the Hadoop process, and you have to specify what tool you're going to use to go out and figure out what are the characteristics of data that tend to predict fraud versus non-fraudulent activity. So that's a common thing that Hadoop gets used for. Email fraud, spam, what's spam, what's real, bank fraud. By the way, if you attempt ever to get detail from people who run fraud detection, none of them ever give you detail about their algorithms. And for good reason, because if I knew what my bank was using to detect fraud, I'd try to do it a different way the next time I defrauded my bank. So you can't find out a lot about these algorithms, but you know that they're in use. Clickstream analysis we've talked about before, so I'm not going to mention it. Search indexing we've talked about before, so I won't mention it. Clustering analysis is really interesting. So here this is kind of a muddled picture. I should have gotten a better picture. But one of the things that you can do in unsupervised learning is we hand it a lot of data points and say, this is called the k-means cluster problem. Divide this up into k, where you specify a value of k, sets, or you specify a limit on what k can be, sets. And what it attempts to do is find, clusters of points that are close together where the distance between the clusters is far apart. Sometimes this is easy. More often than not, it's hard. If you've got a cluster within a cluster, that's really hard to find. But this is an example of something we do. It's a purely descriptive tool. It doesn't tell us anything about it, what's in a cluster, why it is. We've got to figure out, after seeing it, what the interesting things are about that cluster. And here it's drawn in 2 dimensions, but you can do it in 20 dimensions. I tried drawing a 20-dimension one in PowerPoint, but I couldn't do that. So people jumped onto Hadoop. And I'd go into customers and say, they wouldn't say it in exactly these words, but this is what the intent was. I got to get me some of that Hadoop. Okay, it's hyped. It's the greatest thing. It's going to solve all my problems, but it is not nirvana. So, and there are a number of reasons. One, getting data in and out of one of these clusters is cumbersome. It doesn't obey the semantics that we associate with POSIX-compliant file systems that we see in virtually every other operating system. The name node is the place that stores the location of all your data. And how many of them are there in a cluster of 10,000 nodes? 1. What happens if the name node fails? You are in deep, deep yogurt. So there are tools to make this more amenable, but a name node failure brings down the cluster. And if it's not backed up, you've lost all the data. Now, that said, everyone has tools. It's written in Java. Okay? Why? It's an open source project. The open source community loves Java. Java's great for lots of things, but writing operating systems is not one of its strengths, and performance is not good. So it's slow. A little company called MapR Technology has kind of said, we're rewriting this thing in C. It's going to be 3 to 4 times as fast. We're going to put in lots of other stuff that's going to make it more amenable to enterprise-wide computing, including fixing the name node problem. But, in general, the thing you get, the open source version you get from Apache is full of problems. Normally, every data block is duplicated 3 times, so all of a sudden your 2 petabyte database is now a 6 petabyte database. That's a lot of spinning disk. The code base is immature. For years, within the Hadoop community at Apache, there were raging disputes on whether it was mature enough to call the next release 1.0. So we were 2.1, 0.22, 0.23, maybe we're going to call the next one 2.6, and finally they agreed that we were mature enough to call this 1.0. That gives you an idea. MapReduce is really hard to write. I saw on the internet some headhunter was looking for someone with 10 years of MapReduce experience. This product's been out for less than 7 years, but never mind. And performances can be erratic. So what happens? People started putting together applications that included both SQL components and not SQL components. And there are many. I just happen to like this one because it's something you absolutely cannot do in SQL, and it makes use of SQL where SQL is good. So we've got satellite photographs of pretty much every roof in North America, okay? And someone has written a program that actually takes a look at a picture of a roof and figures out what the area is, what the number of ridges are, what the number of valleys are, other things I don't know about roof, how big the chimney is, whether there's flashing around the chimney, et cetera, et cetera. And they do that purely, that image analysis purely in Hadoop. They take the images, they get the geocoding information so they know where that picture is from. They translate that to a street address. The street address, they go and look up in the land records and the tax records and figure out who owns the property, where it is, how much it sold for, etc. And you can buy that. So you want to figure out what the roof on 123 Main Street is. You can go out, I think for $25. You can buy that. Who cares? What's the economic value of that? Well, I'm a roofing contractor, let us say, okay? Joe Smith at 123 Main Street calls me up and says, can you give me an estimate on fixing my roof? And you can say one of 3 things. You can say, yeah, we'll be right over, but that never happens with a roofing company. So you can say, yeah, we'll have a guy over in a couple days. Or you can say, yeah, we'll have a guy over, but by the way, you live 30 miles out of town, and he's 20 miles on the other side of town, so he's got to drive up there an hour. He's got to get up on a ladder, climb the roof, get down, da-da-da. Where for 25 bucks, I can go here and buy that, and with all that statistical information that I've gotten out of my Hadoop cluster, plus what I've gotten in my relational database, figure out what an estimate should be to charge you. And furthermore, I can take a look at that and see which roofs are degrading, and maybe call those people up preemptively and say, you know, your roof's in pretty terrible condition. I think I'd phrase it better if I was in business, but your roof's in pretty terrible condition. You want me to give you an estimate on what, I think we can put you on a new roof for X thousands of dollars. Or if I'm an insurance company, I can go take a look in a neighborhood and see, what's my exposure for roof damage if I'm in a place where there are a lot of hurricanes or tornadoes or things like that. So there's an example of something that's kind of non-standard. And so here, NoSQL doesn't mean no SQL. It means not only SQL, combining SQL and not SQL in a way. We talked a little bit about semantic analysis of sentiment. There are all kinds of things you can do. Here, I don't want to belabor it, but you can run MapReduce jobs for text processing. You can use something called the Python Natural Language Toolkit, or Solar, for examining, the text analytics. You can create histograms. You can see which words match. You can then run k-means clusters to see, what group of documents or tweets or things clumped together, and you can try and then characterize them. If you see words like bug, download, hate this company, that's sort of one cluster. You got another one which is speed, innovation, that's another cluster. So you can do sentiment analysis on this, and that's only half the battle. I have a customer who does the following. You can see that since I don't code well in PowerPoint, this is one I did. All those other slides that have nice graphics are ones I borrowed from someone else. So they get raw data from a variety of places. They get it from text, they get it from videos, they get audio files, they get log files, they get email files, they get tweets. And they run this into a Hadoop cluster, and they extract information. This happens to be a security agency of the United States government. So you can imagine the information they try and collect out of these things. And they try and relate it to a relational database where they have got a table or series of tables of objects of interest. So known people on terrorist watch lists, known subjects, known places, known code words. So if you get a tweet that says, I'll meet you for lunch at Cafe X, that could be innocuous, or Cafe X could be a known code word for something or other, okay? Go through 10, 20, 30, 50 terabytes of data a day, throwing away 99.99% of it, keeping the rest in some kind of storage system. So they keep relational information, but they also keep the interesting stuff, raw data around, in case they have to go back to it later. Or maybe Cafe X doesn't mean anything to me now, but I discover next week that Cafe X is a meaningful term, and I go to it. And then one last thing I'm going to talk about, which is sort of the newest development here and the most esoteric, which is mid-tier in-memory data caches. A lot of companies make one. VMware has one called Gemfire. Oracle has one called Coherence. There's an open source one called Memcached. And what they are large collections, cluster of mid-tier application servers, basically, that they store data in. So these tend to be big memory machines. They replicate this stuff around. And this is very good for doing extremely low latency operations. So stock trading systems run on these kinds of clusters where you need responses back and have to respond to events in milliseconds and possibly microseconds. Nothing Hadoop is ever going to get you anything vaguely like that, okay? But, so these are also in case of if you're doing analytics when you need to do real-time analytics, when neither SQL nor MongoDB or Hadoop or anything else is going to work for you. And so people have taken this and they get source systems, then they run it through a sort of a combiner. And what it does is it takes on the left-hand side and puts that in a real-time data store like a mid-tier memory cache and bulks it up into, then you can do bulk loads into an analytics database of sorts for non-real time. So that's the state of play these days in what's happening in how we do analytics at a high level, okay? But that's only half the problem. One other thing. Doing analytics in the cloud. I forgot to mention this. What is the cloud? Everyone's got a different definition of the cloud. So what I've observed is the following. We have some people who do analytics in the cloud, but generally they don't run very big clusters in the cloud. They start off in the cloud because they don't want to go out and buy hardware, and it's very cheap to run stuff in either an Amazon. There are lots of other companies, but Amazon's the most famous that runs these clouds. And what I found is that people do this mostly for development and testing, but not for production. Okay, when they get to the production phase, it becomes too costly. If you're going to run, something a typical first-order Hadoop cluster, let us say, is 40 nodes. Okay, if you're going to run that on a database cluster, say you're talking 80 nodes. 80 nodes running 24 hours a day of the big-size Amazon machines starts to mount up, and so it becomes an expensive proposition. It's also difficult to import and export data in there, and many cloud providers charge you by the bit for getting stuff in and out. It's sort of like the Gillette razor thing. We'll give you the CPUs for nothing, but we're going to charge you for every little bit of data transfer you do. There's also a big, not invented here, ego issue for people. A lot of people in the Hadoop community like to build their own stuff because it's cool to build your own stuff. Okay? It is not cool to go to Amazon. So. And the last thing is virtualized I/O up to the task? And I think the answer to that is today, no. But from what I've seen of the Intel roadmap, as Intel builds more and more integration into the chip, where pretty soon it's not just the CPU, but you're going to have memory and the system on a chip, I think you'll see that virtualized I/O will perform better, and so all these analytics things will start to run in clouds, possibly private clouds. But in terms of real analytics projects, it's going beyond technology. Technology are not the gating or limiting factors. It's the skill set of people. I go into customers, and I don't want to sound like I'm belittling business intelligence here, but customers think that because they're doing business intelligence, they have got all their analytics problems solved, and that have some of their analytics problems solved, but they certainly don't do much in the way of predictive analytics or some of the newer techniques that you'll see, like k-means clustering or certain kinds of things of that ilk, text analysis in business intelligence. So it requires a skill set that goes beyond that. And they've got lots of good SQL people. But I got to tell you, you can know a lot of SQL and not be able to do any analytics whatsoever. So that's not enough. And so a lot of times you're going to have to do either in-house deployment of your existing resources or go outside and find it. And there are there are a few small, good companies that go out there and will help you get started. They'll show you how to do a first project. They'll build big projects for you. Some of them have engagement models that say, we're not on site for more than 4, 6, 8, 12 weeks. We're never going to be kind of stationed permanently at a customer site. And the other thing, it's really important, is collaborative tools, because in spite of a comment about data science this morning, whether it's a fad or whether it's pretentious, the kinds of tools you need to do and the kind of people you need to do analytics are people who understand these tools, and we call them data scientists. You might call them statisticians in a previous environment, but they're now called data scientists, and they work best when they work collaboratively, okay? In another shameless product plug, the company I work for, Greenplum, has this tool called Chorus. I won't talk about it much, but if you go to greenplum.com, it's a collaborative tool for data scientists to work together, to spin up playpens, to figure out, getting new data sources in, what their experience has been. I can tell you an amusing story I don't have time for how people solved or did not solve the Netflix prize problem by working collaboratively. Application ports are very difficult. So when you move to this new technology, you've got a lot of ways of doing business the old way that don't translate nicely into doing business the new way. And it's very difficult sometimes to move from a traditional environment to an analytics environment, or from a traditional BI environment to a predictive analytics environment for a variety of reasons. How do you get started? So we find that customers of ours who are most successful follow these rules. One, they find a business problem that has monetary value to not the IT department. The IT department, anyone here work for the IT department? Let's assume the answer is no, so I can speak frankly. The IT department frequently gets in your way when you try to do these analytic projects, for reasons I'll mention. So you want to find a business problem. It means you've got to talk to the lines of business users. That's important, but it can't be mission critical, because you've got to account for the fact you may fail the first time, okay? And you want to show success, so you want to find something that's got some value. You can show success, return on investment. You can, for example, take an existing application that's either underperforming or it's not structured in a way that to get questions. Like you built the data schema that somehow makes it extremely difficult to ask the questions if you had built a different data model. So set reasonable expectations. Under promise, over deliver. Don't let them being the people who want the results from this project desperately, don't let them get into scope creep with you. Define what the project is carefully, and don't try and boil the ocean. Don't solve every problem. Don't code at the speed of light for 3 weeks. That's not going to work for you. And if you have to, hire outside expertise for the short term and train your staff. And it pays to train your staff to do this. Why do these analytics projects fail? So sometimes the stakeholders feel threatened. And that is to say, they are used to doing business in the old traditional way. They don't understand this new technology. And excuse me if I'm sounding harsh and cynical, but as you can tell from my accent, I'm from the East Coast of the United States, where people are harsh and cynical. And I'm trying to overcome it, but I can't. But I seriously mean that. You will find people in the lines of business who feel threatened by doing business in the new way. You've got to work your way around that. Sometimes the stakeholders are too timid. They want to change, but we'd like to be able to do this, but we don't have the staff to do this, and we can't really and it won't fit into our schedule. That's probably not a promising sign for being successful in this game. The stakeholders are tied to the past. Okay. To do this project, you need a variety of human resources. You need the analyst, the data scientist. You need the subject matter experts. Data scientists are generally people who've got great analytic skills. They love fooling around with data. They know nothing about forestry. Okay? You need subject matter experts in there with them. You also need a project manager in there, but you've got to draw the line very carefully, because if you get too much project management, you're back in the old way of doing things. But you need to have someone on the team who can get the data that you need, and frequently, other stakeholders in the organization don't give you the data that you need. Sometimes the reasons are legitimate, that they're privacy rules. That said, we can anonymize data now pretty well. Sometimes there are legal reasons, and there are legal reasons, and sometimes they don't want to lose control of the data, because he who controls the data controls the enterprise, and if I give it to you, then I'm going to lose my position of control in the enterprise. And this frequently happens. I know you're shocked to hear this. The other thing people say is, we need to ensure data quality before we start the project. This is death. You ensure data quality by fooling around with the data and examining the data and playing with the data. This is, to my mind, I mean, I understand that, the data governance people, the people who have, Rottweilers and pit bulls and stand there and are reluctant to let anyone in or out of a data warehouse. There's good reason for doing some kind of data governance. But the whole point of doing agile data analytics is you look at the data you got and you figure out what you can use and what you can't use. And then you figure out what needs to be cleaned up and how it needs to be cleaned up. But if you wait for the data to be clean, you will never start a project. Okay? The other people say, we just need aggregates. We don't need the raw data. Okay? Well, there's a lot of stuff that you can do with aggregates, but it cuts out a huge amount of your analysis. Okay? Other people say, we're perfectly happy with reports. All we need is reports. And maybe they're right, maybe they're wrong. Maybe they've got some other agenda here. And also, they don't have enough analytic experience. And we don't have enough, basically, data scientists these days. You find someone who's got a little Hadoop experience and knows how to run a three-way analysis of variance, and that person can afford Larry's yacht in a few years. So, other reason is there's no clear business objective why you're doing this. You've got to have a clear business objective why you're doing this. And if this is going to be the least bit successful, you're going to produce actionable information, and you've got to take action on it. It can't be a report that gets stored in the file drawer or the electronic file drawer someplace that no one does anything with, because then you don't show any value, any return on investment. So that's what I got to say. I don't have any wrap-up slides. That's been my experience, and thank you very much for listening.